All right, so today we're going to talk more about induction, which we discussed last time. So remember, the goal of induction proofs is to prove something like the following, that for all natural numbers, some proposition or some statements P sub n hold. And we looked at one way to do that last time, which we called induction, which was you establish that P sub 1 is true, and then you show that Pn implies Pn plus 1 for any n, and we discussed why that implies that all of the P sub n's are true. So a different way to think about what we're doing in induction. So it turns out to be basically the same thing as induction, is to try to prove all of these propositions by contradiction. So think about proving for all n in capital N P sub n by contradiction. So that is, suppose that it's not the case that for all n in n we have P sub n. Well, that would mean we had the statement there exists an n in n such that not P sub n. All right, so far nothing special. We've just looked at the negation of this of the statement we're trying to prove, and then that gives us that there has to exist some n such that one of our statements doesn't hold. And then in our proof for contradiction, we'd be looking for some to derive some contradiction from the fact that one of these pn's is not true, that we have not pn. But the twist ingredient here, so is to consider the following idea. If there exists an n such that not P sub n holds, then there has to be a smallest natural number n such that not Pn holds. Okay, so consider the smallest such n where we have P sub n, or where we have not P sub n. And call this natural number k. Okay, so then it must be that P sub k is false, because we have not P sub k, and P sub k minus 1 is true. So the utility of considering the smallest natural number where not Pn is true is that, well, we don't just get some random n here such that not Pn is true. We get this P sub k is false. In other words, not P sub k is true, and we can consider that P sub k minus 1 is true. So this, considering the smallest one, allows us to eke a little bit more information out of this statement up here. Now there's one slight hiccup here. So let's address that now. Slight hiccup is k could be 1. so that p sub k minus 1 doesn't exist. Doesn't even make sense. And in which case this this idea of considering the smallest such n doesn't really help us. So if k is equal to 1, then that would, in that case, that would say that all of our propositions that we're looking at are false. So as part of this method, if you want to use the method that we're talking about, you're going to have to establish that p sub 1 is not false first. In other words, you're going to have to establish a base case here. Okay, so that leads to the following method here. So this is called the method of smallest counterexample. Okay, so here you're trying to prove that for all n in n, some list of propositions is true. So the first step is the base case. You show that p sub 1 is true. So first show p sub 1 is true. So establish the base case. Two is you suppose, for the sake of contradiction, that at least some p sub n is false, and consider the smallest n for which this is true. So for which p sub n is false. Say p sub k. And note by 1, k is strictly bigger than 1. So p sub k can't be the base case. And then 3, thus the prior proposition to pk, i.e. p sub k minus 1, is true. So then use that p sub k minus 1 is true and p sub k is false to derive a contradiction. So basically, in summary, you prove P1, then assume that you have p sub k minus 1 and not p sub k for some k. Then assume that that holds. for some k. So that k was the minimal k such that that not pk is true above. And this and here, oh yeah, so you assume that for some k and then derive a contradiction. And this thing here, this is just the negation. So another way to say this is it's the negation of the negation of pk minus 1 and not pk. But the negation of that conjunction there is exactly the implication. So this is the same thing as not p sub k minus 1 implies p sub k. I remember what we did in our standard discussion of induction last time was, so what you did in induction is you prove P1 and then you prove that Pn implies Pn plus 1 for any n, right? So we see here that the logical structure of what we're doing in this method of smallest counterexample is exactly the same as in induction. Because really what we're doing is we're still establishing the base case, and then in order to establish that Pn implies Pn plus 1 for all n, we're just proving that by contradiction. We're assuming that that's not the case for all n, right? So in particular, for n equals k minus 1 here, so it's not the case that that implication holds, and then deriving a contradiction from that. So they really have the same logical structure as standard induction. So, you want to note this is this has the same logical structure as standard induction. Okay, so basically it's probably for any induction proof you can rephrase it as a method of smallest counterexample and vice versa. So here is an example. So our proposition is if n is a natural number, then 4 divides 5 to the n minus 1. And you'll find a standard induction proof of this very straightforward, but here we'll give a proof by method of smallest counterexample. So I'll just show you how to write that out. So note the theorem is true for n equals 1 since 4 divides 5 to the 1 minus 1, right, because that's equal to 4. So a base case is established. Now suppose the proposition does not hold for all n, and let k be the smallest natural number for which this is the case. Then 4 does not divide 5 to the k minus 1, but 4 does divide 5 to the k minus 1 minus 1. Okay, so the first thing that 4 does not divide 5 to the k minus 1 doesn't really give us anything, but the second thing does. So thus 5 to the k minus 1 minus 1 is equal to 4 times L for some L, which is going to be a natural number. And then to get 5 to the k involved, we'll just multiply this by 5 on both sides. So therefore 5 to the k minus 5 equals 20L. And then to make 5 to the k minus 1 appear, which is equivalent to, we'll just add 4 to both sides, which is equivalently 5 to the k minus 1 equals 20L plus 4. And now we'll get a contradiction because clearly this right-hand side, we can pull 4 out. So that's equal to, equal to 4 times 5L plus 1. Right? So we see that 4 divides 5 to the k minus 1, but we assumed 4 did not divide 5 to the k minus 1. So this contradiction proves the proposition. Okay, so that's how you use the method of smallest counterexample. Okay. So now we're going to move on and talk about strong induction. So our initial discussion of induction was like this. We sort of imagined our propositions as dominoes. So you had P1, P2, and Pn plus 1, ... right? And the basic idea is that if we can make this Pn fall down, so fall down and knock into that Pn plus 1, then Pn plus 1 would knock down and hit Pn plus 2, and etc. down the line. And all we have to do to start a cascade like that is to knock P sub 1 down. So if we knock P sub 1 down and hit P sub 2, that'll get this chain reaction going and go all the way down the line. Right? So we just had to prove that P1 holds, P1 is true, and that Pn implies Pn plus 1. So this one gets your, so this one shows that a chain reaction is possible, and this one gets your chain reaction started. So that's the basic idea. But in practice, this might be only, so this sort of schematic of induction that we've discussed before might be too narrow a way of proving all of the propositions Pn, because the ultimate goal is to prove for all n Pn holds. And this is one way of doing it, the induction that we discussed last time. But it's not necessarily the only way of doing it. It's sort of the simplest way conceivable of doing it. So you can imagine other things, like, for example, so if I just sort of do the same kind of schematic, you could imagine a situation in which Pn minus 1, Pn plus 1. And in this case, the dominoes analogy kind of starts breaking down. But you can imagine that perhaps it's possible that Pn plus 1 is not implied by Pn, but is implied by Pn minus 1. And then Pn would be implied by Pn minus 2. And P4 would be implied by P2. Right? And P3 would be implied by P1. And then in such a case, right, since P3 is implied by P1 and does not imply P2, so you might notice that there's no arrows coming into P1 or P2, right? So we would need both of these as base cases if this was the situation, that each Pn plus 1 was implied by the ones 2 before that instead of the one directly before it, like in standard induction. And there's no reason to think that that it might be the case. So there's no reason to think it couldn't be the case that your Pn plus 1 is implied by the thing 3 before it, or 4 before it, or 5 before it, right? And if that were the case, that was always say like that Pn plus 1, if that was implied by P sub n minus k, so this would be the thing, so this is k plus 1 steps earlier. So if that was the case, then your base cases would have to go all the way out to k plus 1, from P1 to P sub k plus 1. So you would have to change the picture here a little bit. Right, because if every proposition is implied by the one k plus 1 steps earlier, well, there is nothing k plus 1 steps earlier for any of the propositions through P1 through P sub k plus 1. So you would have to establish all of those as base cases. And it could be that things are even more complicated than that. So it might be that you're looking at P sub n minus 1, P sub n plus 1. It might be that your Pn plus 1 is implied by both of the previous two propositions. And so it could be that one needs that Pn, so maybe I'll say it this way. So it could be that Pn implies Pn plus 1, that you can't do that, and that you need instead maybe Pn minus 1 and Pn. And maybe only those two together have the force necessary to imply Pn plus 1. Right? Or maybe it's Pn minus 1 and Pn minus 2. Right? Or maybe some even more complicated situation. Maybe it's maybe you need Pn minus 1 and Pn minus and Pn minus 3. So maybe you only need some certain collection of the previous previous propositions in order to get p sub n plus 1. Okay, so there's all these kind of complicated potential situations, but they're all covered by the following general situation. So it helps to imagine dominoes again. So you have P1, P2, P3, up to some Pk, and then ... Pn plus 1. And so again, we're trying to establish that that all of these propositions are going to fall down. And so as we were saying up there, it might not be the case that p sub n plus 1 is implied just by p sub n. You might need some potentially earlier proposition or even multiple earlier propositions in order to prove p n plus 1. So you might need the weight of at least multiple previous of the dominoes to knock down p sub n plus 1. So you might like to think about it this way, that when you have dominoes falling, so you have this first domino knocks into the second one, right? And then the second one tips over and knocks into the third one. Well, it might not just be that this third one is knocked down by the second one, because it's really, you have the first two dominoes, sort of the weight of both of them knocking into the third domino if they're like spaced together enough. So maybe it wasn't that P3 was knocked down by P2. Maybe it was P1 and P2 knocking down P3. Right? And then once P3 falls and knocks into P4, well, maybe P3 knocks P4 down, but maybe it was actually that P1, P2, and P3 knocked P4 down, right? So if you can start a cascade of dominoes, then you can assume that you have all of the force of the previous dominoes, right? So if I want to knock down this domino here, right, I can assume that I have the force of all of the weight of all of the previous dominoes, right? All of them have been knocked down if I've started a cascade. And so I can assume that I have the weight of all of them behind me in order to knock down the n plus first domino there in the picture. So that's the basic idea of strong induction. So strong induction sort of informally is show you can start a cascade of the dominoes and use the full weight of all previous dominoes to knock over any given one. Okay, so that's kind of the way you can think about this strong induction. So here's the proof technique more formally. Okay, so in the first case, so you establish P1 through Pk for some k. Okay, so that's showing that you can start the cascade, right? You can knock down at least the first so many dominoes. And then you show that P1 and P2 and ... and Pn, right? So that's the weight of the first n dominoes. Show that that knocks down the n plus first. So this principle of induction tells you that if you're trying to prove this step right here where you show that p sub n plus 1 is implied. And in standard induction, you do that just by assuming p sub n, right? But this principle of strong induction says you're allowed to assume any or even all of the previous propositions before p sub n plus 1. Okay, so so that covers all of the cases that we talked about up here. Right? So for these ones where your proposition was implied by the 1, 2 behind you, well, if you assume that you can use the full weight of all of the propositions before, right? Then that covers the case that case where you just need this one particular one, and it covers this case here, right? So if you need the 2 previous propositions to prove any given proposition, well, assuming the full weight of all of the previous propositions, that certainly covers that case as well. All right, so all of those potential special cases that we discussed before that you might worry about are covered under this principle of strong induction. All right. So let's look at a proposition that uses strong induction. So if n is a natural number, then 12 divides n to the 4th minus n squared. So n to the 4th minus n squared is always divisible by 12. And the proof is going to be by strong induction. So it's going to turn out that if we want to show a given proposition p sub n plus 1 is true, that actually we have to go back 6 steps to p sub n minus 5. So any given proposition is going to be implied by the one 6 steps before it. All right, so the fact that we need to go back 6 steps is going to mean that we need to verify P1 through P6, right? Since there's no propositions that are 6 steps before those. So we're going to have 6 base cases to establish, and then each of those are going to imply the ones 6 after them. So we'll see that allows us to conclude the proof by strong induction. Okay, so that's why I'm about to do the base cases, so I'm going to explain why we have to do all of these base cases. Okay, so the proposition. So we proceed by strong induction. And eventually you'll probably just drop the adjective strong, and so it probably suffices to say just induction. If you're reading a proof, you might just see the word induction and not the word strong. And sometimes people, instead of saying strong, say complete induction. So that's another synonym that you might see. So first note that the proposition is true for n equals 1 through 6. Okay, so for n equals 1, we have 12 divides 1 minus 1, which is 0, and that's true. For n equals 2, we have 12 divides 2 to the 4th is 16 minus 4, So that's 12. Certainly that's true. N equals 3. We have 12 divides 81 minus 9, which is 72, and that's true. 12 times 6, 72. N equals 4. We have 12 divides, let's see, 256 minus 16 is 240, and that's 12 times 20. For n equals 5, we have 12 divides, 5 to the 4th is 625 minus 25 is 600, and 600 is 12 times 50. And last one, n equals 6, we have 12 divides, 36 times 36 is 1296, minus 36 is 1260, and that is 12 times 105. Okay, so that all works out. So now assume that the proposition is true for n equals 1 through k, where k, we can assume k is greater than or equal to 6, right? Because we proved those first 6 cases, and we'll show that it holds for k plus 1. Now, as I said above, we will show that the proposition for k plus 1 follows from the proposition for k plus 1 minus 6, that is k minus 5. So since k is greater than or equal to 6, k minus 5 is greater than or equal to 1. So k minus 5 is a natural number for which the proposition is true. Okay, so now we compute what we compute is the quantity where n equals k plus 1. So we look at k plus 1 to the 4th minus k plus 1 squared. And right, we're going to relate this to k minus 5. So I want to write this as k minus 5 plus 6 to the 4th minus k minus 5 plus 6 squared. And to prevent this from becoming too annoying, I want to call k minus 5 L. So I'm just going to rename this L. So this is L plus 6 to the 4th minus L plus 6 squared. And maybe I should make a note of this above. So now we compute where we denote k minus 5 by L. Okay, so now we have this this to compute, and Well, you gotta do this fourth power of L plus 6. So what that comes out to be is L to the fourth. So that's L to the fourth plus 4 times L to the third times 6. Okay, so this 4 is a coefficient that comes out when you do all of the, so this 6 here, that's that 6. And you have L to the third. This 4 is just a coefficient that comes out because you get 4 copies of L to the third times 6 when you expand all this out. Okay, so the next one is you get 6 times L squared times 6 squared. Then you get 4 again times L times 6 cubed, and then you get 6 to the fourth. Okay, so you have that, and then you have minus, and this one's easier, everybody knows the FOIL, so we have minus 12L minus 36. Okay, and remember, so we know the proposition holds for k minus 5, which is L. So we know that L to the fourth minus L squared is divisible by 12. Right? So we'll write that this equals L to the fourth minus L squared. So that's this term and this term here. And then we would just like to put a factor of, we'd like to see a factor of 12 in everything else. So let's just clean this up a bit. Let's see, the L cubed term, we can write that as 12 times 2L cubed. And then we have the L squared term here, and let's see so we already have the 6, and if we pull it, we have a 6 here, and if we pull a 2 out of one of those 6s, that gives us 12, and then 3 times 6 is 18. 18L squared. Then we have the L terms here. So we have plus, so we have this 12 there, so that's good. And then we want to make a 12 out of this 4 and this 6 cubed. So we need 4 times 3, so we'll pull a 3 out of one of those 6s. So after we do that, 12 times, let's see, we pulled a 3 out of one of those 6s, so we have 2 times 6 squared, so that's going to be 72 minus, then we're going to have the minus 1 because we had this minus 12 here as well, times L. And then our constant, so our constant 6 to the fourth, so we can pull a 12 out of that, one of the 6s, and then a 2 from the other 6. So one of the 6s that'll leave us with 6 to the third, and then pull a 2 out, and we'll have 3 times 6 squared. So that'd be 3 times 6 squared minus 3, because 36 here is 12 times 3. Okay, so that leaves us with L to the fourth minus L squared plus 12 times this whole thing, 2L cubed plus 18L squared plus 71L plus 3 times 6 squared minus 3. I mean, I don't care that much about the details, as long as we pull that factor of 12 out. That's going to be the key thing. Then, since we know 12 divides L to the fourth minus L squared, because L is K minus 5, and we were assuming that our proposition, we know our proposition holds for K minus 5. And since we know that, we can write L to the fourth minus L squared equals 12 times J for some J. And we see that K plus 1 to the fourth plus K plus 1 squared equals 12 times J plus this whole thing, 2L cubed plus 18L squared plus 71L plus 3 times 6 squared minus 3. So K plus 1 to the fourth plus, oh no, I realized I wrote plus here when I meant to write minus. Minus K plus 1 squared is divisible by 12. Which completes the proof. Okay, so that's how your complete induction works. You establish however many base cases you need, and then to prove any given one of your P sub n's, you're allowed to assume all of the ones before them, the full weight of all of the dominoes that have fallen before in order to prove that. Okay, so now we're going to pull all these techniques together for somewhat less frivolous application. So application of induction techniques. To number theory. So we'll actually give a proof of the fundamental theorem of arithmetic. Okay, so here's a proposition, and sometimes this is called Euclid's lemma, and this is really the key lemma. So this is a key lemma to proving the fundamental theorem of arithmetic. So in Euclid's lemma we have, so suppose a1 through an are integers, and n here there's at least two of them. If p is a prime, and p divides this product, the product of all of them, a1 through an, all multiplied together, then p has to divide at least one of them for some I. Okay, so the proof is just by induction. So our base case is going to be, since our n is bigger than or equal to 2 here, our base case is going to be when n equals 2. So the base case, well, so our base case will be when n equals 2. So suppose p divides a1 times a2. So we need to show P divides A1 or P divides A2. Right, we're claiming that P divides one of these two integers, A1 or A2. Well, it's either the case that P divides A1 or it doesn't, right? So it's either that P divides A1 or P doesn't divide A1. In the former case, we're finished. So suppose that P does not divide A1. This implies that GCD, the GCD of P and A1, of P and A1 is equal to 1. And why is that? Well, the GCD has to be a common divisor of P and A1. In particular, it has to divide, or it has to be either 1 or P, since P is prime. Okay, so the GCD has to be either 1 or P, right, because it's dividing P. But it can't be P because the GCD being a common divisor has to also divide A1, and we just said that P does not divide A1. So it has to be either 1 or P since P is prime, but it can't be P since the GCD divides A1, or I guess I'll say and, I already said but in the beginning of the sentence, and P does not divide A1. Okay, so P not dividing, if you have a prime not dividing a number, then the GCD of the prime with that number has to be 1. Okay. So what do we get from that? Well, the GCD is expressible as the linear combination of the two things involved. So thus, P times U plus A1 times V is equal to 1 for some integers U and V. And now just remember what we're trying to do. We're trying to show that that P divides A2, right? We're assuming that P doesn't divide A1. We're showing that P does divide A2 in that case. Well, we have this equation that says something equals 1. I can make that an equation that says something equals A2 easily by just multiplying both sides by A2. So multiplying this by A2 on both sides gives, so the right-hand side I'll now put on the left, that's just A2, and then we have PU times A2 plus A1A2 times V, and A1A2, well, that's divisible by P, right? So this is P times U times A2 plus P times, let's say, L times V, right? And that's So I'll just give a reason for this. So since P divides A1 times A2 implies that A1, A2 equals P times L. And so pulling the P out, and thus P divides A2 as claimed. Okay, so this is our first instance of a non-trivial base case. So the base case is established. Okay, so now we will use induction. We'll use our induction hypothesis. So suppose the proposition is true for some n bigger than or equal to 2. So we'll try to prove it for the case of n plus 1, and so we'll be looking at P divides A1 times ... AN times AN plus 1. Okay, well, the cool thing about this proof is you use the base case again, and then you use the inductive hypothesis. So note that A1 times ... AN plus 1, that equals, if we just group the first n things together, this is just a product of these two numbers, right? So you think about this thing as just one number, and then that's some other number. So by the base case, So by the base case, P either divides A1 ... AN, or P divides AN plus 1. So in the latter case, we're done. We're done immediately. While in the former, we apply the induction hypothesis and conclude that P divides AI for some I such that I in this case would be between 1 and n. In any case, P divides one of the A sub I. Where I is between 1 and n plus 1 now, which completes the proof. Okay, so that's the standard proof of Euclid's lemma, using the fact that the GCD is expressible as an integer linear combination of the given integers, and then once you've established the case with two integers, then it's a typical proof by induction, to extend that to the product of n integers. Okay, and this is integral to the proof of the fundamental theorem of arithmetic. Okay, so here's the fundamental theorem of arithmetic. I've mentioned this before in class. So here's the theorem. Fundamental theorem of arithmetic. And the fundamental theorem of arithmetic is the thing that says that every natural number can be written as a product of prime numbers, and that product as prime numbers is essentially unique. Okay, so here's the statement. So any integer n greater than 1, so we don't allow 1. It has a unique. I mean, one isn't prime, so 1 isn't prime by definition, and can't be written as a product of prime numbers because all the primes are bigger than 1. So. Okay, so it has a unique prime factorization, and unique here means that if n equals p1 ... through pk, and also equals q1 ... through ql, and so k and l might be different. I mean, so it's conceivable that there might be some natural number, right? Maybe really large that you've never thought about sufficiently hard, that could be factored into, I don't know, 6 different prime numbers, and then have a different factorization into 7 different prime numbers. So you have to consider that possibility, that if these are 2 prime factorizations, are 2 prime factorizations, then k in fact equals L, and each pi equals some qj, which is just to say that these the list of p's is the same as the list of q's, they just might be in a different order. Okay, so the only way you can get a distinct prime factorization is by just doing the trivial thing where you just sort of switch the order in which you're multiplying them around. Otherwise, the actual list of them is the same. So that's the unique part. Okay, so that is the theorem. And here is the proof. Okay, so there's 2 parts to the proof. So we have to show that any integer greater than 1 has a prime factorization, and then we have to show that it's unique. So we first show that n bigger than 1 has a factorization into primes. Okay, so this is so we proceed by strong induction. So clearly, since n equals 2 is prime, we've established a base case. And any prime number is a product of primes. It's a product with only one thing in the product. Okay, so we've established a base case. Now suppose 2 dot 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 up to n have factorizations, have prime factorizations. And consider n plus 1. So here's the little trick. If n plus 1 is prime, we're done. So the trick is to consider two cases, that n plus 1 is prime and n plus 1 is not prime. So if n plus 1 is prime, we're done. And for the same reason we were done in the base case for n equals 2. And any prime is a product with one element in it of primes. If not, then, well, what does it mean to not be prime? It means that it's a product of two natural numbers which are between 1 and n plus 1. So then n plus 1 equals k times l, where k and l are both strictly between 1 and n plus 1. And I guess I should just say that k and l are natural numbers, just to be pedantic about it. Okay. Well, k and l are less than n plus 1, right? They're in the range 2 to n. Okay, so thus the induction hypothesis. The induction hypothesis thus applies to k and l. So they are products of primes. So let's say, so k might be p1 dot 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 p sub I, and k might be q1 dot 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 q sub j. So then n plus 1 is k times l, that's p1 times dot 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 pi, q1 dot 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 qj, is then clearly a product of primes, right? All the p's and all the q's are primes. Is clearly a product of primes. Okay, so that completes the proof of the existence of a factorization. So this completes the proof of the existence of a factorization. Okay, so we now show uniqueness. And we proceed by the method of smallest counterexample, by the method so clearly n equals 2. So 2, I mean, all the other primes are bigger than 2. So 2 can't possibly be a product involving primes bigger than itself, or any numbers bigger than itself. So clearly n equals 2 has a unique prime factorization. So a base case is established. So now assume that not every n greater than 1 has a unique prime factorization. And let k be the smallest such number where this is the case. Actually, I changed my mind. I want to call this M. Okay, so thus M equals P1 through Pk and also equals Q1 through QL. Okay, and now the key here is to apply Euclid's lemma. So we note that P1, since P1 is involved in this product, if we look at Q1 through QL, we find out that P1 divides the product Q1 through QL. Right, so P1 divides M, and M is Q1 times dot 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 up through QL. So that means P1 has to divide that product. So we note that P1 divides Q1 dot 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 QL, and applying Euclid's lemma, we find that P1 divides Qi for some I. Since Qi's only divisors are 1 and Qi, and P1 does not equal 1 because 1 is not a prime, right? P1 is a prime, Qi is a prime. So Qi being prime means that it has only these two divisors, and P1 being prime means it's not 1, so it must be that P1 is equal to Qi. Right, so you got P1 dividing Qi, and P1 can't be 1, so we're forced to conclude it's the other divisor of Qi, which is just Qi itself. So P1 equals Qi. By canceling P1, we obtain P2 times dot 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 Pk equals Q1 dot 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 Qi Qi hat. I think I introduced this notation before. This means Qi here has been removed. Okay, so we obtain this equality and call this number with these two different expressions, call this M prime. So we obtain M prime, which is less than M, right? Because we divided by something bigger than 1. Okay. But then M prime has two distinct prime factorizations. right? So these prime factorizations, they have to be distinct. So we're assuming that the P1, the list P1 through PK and Q1 through QL is distinct. But then we found out that P1 actually agreed with QI, right? So it couldn't be that. So after we remove P1 from the one list and QI from the other list, so that was a place where they did agree. So they have to still disagree at the other ones, right? So the place of disagreement must have been among the P2 through PK and the Q's that weren't QI. Okay, so these actually do have to be distinct prime factorizations of M prime. So returning to this line, but then M prime has two distinct prime factorizations and is less than M, which was supposed to be the smallest such integer, smallest such natural number. So we have a contradiction. And this completes the proof. Okay, so that is going to do it for our treatment of induction. There are some other examples in the book which you might enjoy looking at. One from a domain of math called graph theory. And then there's another little minor proposition in there that's proven by induction, by using strong induction. And then there's some stuff about the Fibonacci numbers, but I don't think we're going to make time for that. All right, so that's all for me for now.